Hey everyone, I think that is everyone that will join. So let's start with today's lecture. We will continue with accretion disks. So yesterday we finished off with the evolution of binary stars and how the one star can steal mass from another star. Does anyone have questions on that, or would you like me to continue? I take that. Let's continue. So the next interesting topic we are going to discuss is accretion disks. So matter flowing from one star to another can't fall directly into the star. Rather, because of the conservation of angular momentum, it must flow into a whirling disk around a star. And the same holds for a black hole as well. So if we take this for an example in this visual representation, we have the one star and matter is falling onto the other star, but that will happen via an accretion disk, and that is due to the conservation of angular momentum. So angular momentum refers to the tendency of a rotating object to continue rotating. All rotating objects possesses some angular momentum, and in the absence of external forces, an object conserves its total angular momentum. An ice skater takes advantage of conservation of angular momentum by starting a spin slowly with her arms extended and then drawing them in. As a mass becomes concentrated close to the axis of rotation, she spins faster and faster, and the same effect causes the slowly circulating water in a bathtub to spin a whirlpool as it approaches the drain. So this is just an example of the conservation of angular momentum. So when you're spinning an ice skating ring with your arms stretched out, you spin more slowly, and with your arms more closer to your body, you spin faster. Mass transferred through the inner Lagrange point in a binary system towards a star must conserve its angular momentum. If the star is small enough, as in the case of a white dwarf, the mass will form a rapidly rotating whirlpool called an accretion disk. Two important things happen in an accretion disk. First, the gas in the disk grows very hot due to friction and tidal forces. The disk also acts as a brake, shifting angular momentum outward in the disk and allowing the innermost matter to fall into the white dwarf. The interior parts of an accretion disk around a white dwarf are violent places. The temperature of the gas can exceed 1,000,000 Kelvin, causing the gas to emit X-rays. And the matter falling inward can produce a vast explosion when enough accumulates on the white dwarf. The explosion of this material hardly disturbs the white dwarf and its companion star. Mass transfer quickly resumes and a new layer of fuel begins to accumulate. How fast this fuel builds up depends on the rate of mass transfer. You can expect novae to repeat each time as explosive layers accumulate. Many novae take thousands of years to build an explosive layer, but some take only decades. At the beginning of this chapter, you read that the word nova refers to what seems to be a new star appearing in the sky for a while and then fading away. Modern astronomers know that a nova is not a new star, but an old star flaring up. After a nova fades, astronomers can photograph the spectrum of the remaining faint point of light. Invariably, they find a short period spectroscopic binary containing a normal star and a white dwarf. A nova, evidently an explosion involving a white dwarf. Nova explosions occur when mass transfers from a normal star through the inner Lagrange point into an accretion disk around a white dwarf. As the matter loses its angular momentum in an inner accretion disk, it settles onto the surface of the white dwarf and forms a layer of unused nuclear fuel, mostly hydrogen. As the layer deepens, it becomes denser and hotter until the hydrogen fuses in a sudden explosion that blows the surface of the white dwarf. Although the expanding cloud of debris contains less than 0.001 solar mass, it is hot, and its expanding surface area makes it very luminous. Nova explosions can become 100,000 times more luminous than the Sun. As the debris cloud expands, cools, and thins over a period of weeks and months, the nova fades from view. In this image is Nova T Pisces erupts every 2 decades, expelling shells of gas into space that Hubble Space Telescope image shows in detail. The shell consists of knots of excited gas that presumably form when new shell collides with a shell from a previous eruption. So note that this system, depicted in figure 10.12, this artist's representation, its name designates the third variable star discovered in the constellation, or in other words, the compass. So, putting this together, what will be the end of Earth when the Sun reaches the end of its life? So, astronomy is about us. Although this chapter has discussed the deaths of stars, it has also been discussing the future of our planet. The Sun is a medium-mass star and must eventually die by becoming a giant, possibly producing planetary nebula and collapsing into a white dwarf that will spell the end of Earth. Mathematical models of the Sun suggest that it may survive as an energy-generating star for additional 8 billion years, but it's already growing more luminous as it fuses hydrogen into helium. In a few billion years, it will exhaust hydrogen in its core and swell into a giant star about 100 times its present radius. The giant Sun will be about as large as the orbit of Earth. So that will mark the end of our world. Whenever expanding suns becomes large enough to totally engulf Earth, its growing luminosity will certainly evaporate Earth's oceans, drive away the atmosphere, and even vaporize much of Earth's crust. While it is a giant star, the Sun will lose mass into space. This mass loss is a relatively gentle process, so any cinder that might remain of Earth would not be disturbed, although its orbit will grow larger and the Sun's mass decreases. If anything is left of Earth after the Sun becomes a giant, it will witness the Sun's final collapse into a white dwarf. So when we put this into perspective, in about 7.5 billion years, the Sun will engulf Mercury and Venus as it becomes a giant. And in 7.59 billion years, the Sun is a red giant and has 0.8 solar mass, and it will completely engulf Earth. So that brings us to quite a scary story of how Earth will end. So then the only thing that will remains is the charred Earth. And that is why I said in yesterday's lecture, for us as a human species to survive, that is why we need to become an interplanetary species. And that is why we need to set up colonies and wander into further regions in our solar system. Do you guys have any questions so far? Can everybody still hear me? So you've seen that low and medium mass stars die relatively quiet as they exhaust the hydrogen and helium and then drive away the surface layers to form planetary nebula. In contrast, massive stars live spectacular lives and then destroy themselves in violent explosions. So right now, currently, we have done the first branch. So a star forms in a stellar nebula, it emerges as an average star, becomes a red giant, collapses in on itself into a planetary nebula, and then the only thing that remains is a white dwarf. But now we're going to look at the second path. We're going to have the stellar nebula, it forms a massive star. The massive star will become a red supergiant. The red supergiant will go supernova. And then from that supernova explosion, what is left will either be a neutron star or a black hole. And now we're going to talk about what is the contributing factors that will determine if we have a neutron star or a black hole. But to determine it, we need to understand nuclear fusion in massive stars. Stars on the upper main sequence have so much mass to die as white dwarfs, but evolution begins much like that of lower mass cousins. They consume the hydrogen in their cores and ignite hydrogen shells. As a result, they expand into giants, or for the most massive stars, supergiants. Next, their cores contract and fuse helium. First on the core and then a shell producing a carbon-oxygen core. Unlike medium mass stars, the massive stars do become hot enough to ignite carbon fusion at a temperature of about 1 billion Kelvin. Carbon fusion produces more oxygen and neon, and as soon as the carbon is exhausted in the core contracts and carbon ignites in a shell. So we've talked about these flashpoints yesterday. So the pattern of core ignition and shell ignition continues with fuel after fuel, and the star develops the layered structure as shown in the figure below. So here we will have in a massive star, we'll have an iron core. Here we have a hydrogen fusion shell, helium, carbon, neon, oxygen, silicate, iron. And we have one layer on top of another layer until we reach iron. Iron cannot be fused. And I said that many times before. The fusion reaction to fuse iron uses more energy than what it actually produces. And that is where reaction stops in a giant star. So with hydrogen fusion in a shell above helium fusion shell and above carbon fusion shell and so on. After carbon fuses, oxygen, neon, magnesium fuse to make silicon and sulfur, and then the silicon fuse to make iron. The fusion of these nuclear fuels goes faster and faster as the massive star evolves. Recall that massive stars must consume their fuels rapidly to support their great weight. But other factors also cause the heavier fuels like carbon, oxygen, and silicon to fuse at increasing speeds. Hydrogen core fusion will last about 7 million years in a 25 solar mass star. But its same star will fuse oxygen in its core in 6 months and silicon in a day. So that is actually quite scary. So here we can see a table of heavy element fusion and a star with 25 solar masses. So that means 25 times the mass of our own sun. And we can see here fusing hydrogen takes 300 million years, which is actually also faster than our own sun. Helium takes about 40 years. Carbon 6 years, oxygen 0.5 years, silicon a day. So that is actually quite scary. So that means the larger a star is, the faster it fuses elements. So hydrogen to helium, 7 times 10 to the power 6 years, helium to carbon, carbon to oxygen 600 years, oxygen to silicon 6 months, silicon to iron 1 day. And then the entire collapse of this star, where it is now compressed into a neutron star or a black hole, takes a quarter of a second. And that is why that explosion is so violent. So theoretical models of evolving stars combined with nuclear physics allow astronomers to describe what happens inside a massive star when the last of its nuclear fuel are exhausted. The death of a massive star begins with iron nuclei and ends in cosmic violence. As a star develops an iron core, energy production begins to decline, and the core contracts. For nuclei less massive than iron, such contraction heats the gas and ignites new fusion fuels. But nuclear reactions involving iron remove energy from the core in two ways. Firstly, the iron nuclei begin capturing electrons and breaking into smaller nuclei. The gas is so dense, it is degenerate, and the degenerate electrons help support the core. So the loss of some of the electrons allow the core to contract even faster. Secondly, temperatures are so high that the average photon is a high-energy gamma ray, and these gamma rays are absorbed by atomic nuclei, causing them to break into smaller fragments. The removal of the gamma rays, heavy, also allows the core to contract even faster. Although the core of the star can't generate energy by nuclear fusion, it can draw on tremendous energy stored in its gravitational field. As the core contracts, the temperature shoots up. But it is not enough to stop the contraction, and the core of the star collapses inward in less than 1/10 of a second. The collapse of the core produces an immense supernova explosion, in which the star's outer layers are blasted outward. The core of the star must quickly become a neutron star or a black hole, the subjects of the next chapter. So here we can see how this is simulated. So the core of a massive supergiant has begun to collapse, as in the lower left corner, and matter continues to fall inward, the blue and green, as the core expands, and outward yellow, creating a shock wave. To show the entire star at this scale, the stage would have to be 30 kilometers in diameter. So only 0.4 seconds after beginning the violent convection in the expanding core, and red pushes outward. So the shock wave will blow the star apart as a neutron star forms in the extreme lower left corner. And here we can see how a supernova explosion looks like. So this is actually very pretty to see. So we can also look at a next picture of another supernova remnant. So remnant is a meaning what remains. So this is a supernova remnant of a star that went supernova. But we can analyze these outflowing gases. So when we look at this supernova, we can break it up. So here we can see red as silicon, yellow as sulfur, greenish as calcium, purple as iron, and the blue is the blast wave. So here we can see this is where the beautiful colors comes from. But now we can also classify different supernova. And this is also something important for the test and exams. I can ask you to classify a supernova for me and ask you what a definition is of the different types of supernova. So supernova occurs when a star with a degenerate core collapses. But astronomers have found different kinds of supernova. Those that do not have hydrogen lines in their spectra are called type 1 supernova. And those that have hydrogen lines are type 2 supernova. So please remember these two distinctions. A massive star with a degenerate core can collapse and produce a supernova. These are called type 2 and contain hydrogen lines in the spectra because their massive stars contains lots of hydrogen. But there are other ways a star with degenerate interior can collapse. A supernova can occur if a white dwarf in a binary system gains mass from its companion, exceeds the Chandrasekhar limit, and collapses. The interior of the white dwarf is degenerate, and as the collapse begins, temperature and density increase in the carbon-oxygen core begins to fuse. Because the gas is degenerate, there is no thermostat to regulate the fusion, and the entire white dwarf fuses suddenly in a violent explosion classified as a type 1a supernova. The much less common type 1b supernova can occur if a massive star loses its hydrogen-rich outer layers to a companion star. The remains of the massive star can develop a degenerate core and collapse, as described in a previous section, producing supernova explosions that lack hydrogen lines. A type 1b supernova is just a type 2 supernova in which the star has lost its outer layers. Because supernovae are so rare, they are difficult to observe. Astronomers must depend on historical records. Some records go back centuries, but more recent supernovae give astronomers the best evidence against which to test their theories. In the year 1054, Chinese astronomers saw a guest star appear in the constellation we know now as Taurus. It became so bright it was visible in the daytime for a month and took nearly 2 years to fade from sight. At the site of the ancient supernova, modern telescopes reveal a many-legged nebula known as the Crab Nebula. Doppler shifts showed that the nebula is expanding at 1,400 kilometers per second, and it is now about 1.4 parsecs in radius. Remember, 1 parsec is 3.2 light years. So dividing distance by velocity reveals that the nebula began expanding 9 or 10 centuries ago, about when the guest star was first seen. The hazy glow inside the expanding filaments of the Crab Nebula is synchrotron radiation that is produced by high-speed electrons spiraling through a magnetic field. So here we can see the Crab Nebula. So the Crab Nebula is also one of the nebula that has been quite thoroughly documented and studied. So this glow we can see is produced by synchrotron radiation. So the Crab Nebula is located in the constellation we know as Taurus the Bull, just where Chinese astronomers saw a brilliant guest star in the year 1054. Over tens of years, astronomers can measure the motions of the filaments as they expand away from the center. Doppler shifts confirm the near side of the nebula is moving toward Earth. And high-speed electrons produced by the central neutron star spiraling through magnetic fields and produce the foggy glow that fills the nebula. Most supernovae are seen in this galaxy. So in this image, the robotic telescope search every night for supernovae flaring in other galaxies. And when one is seen, astronomers can contain spectra as well as record the supernova rise and decline in brightness to study the physics of exploding stars. If a supernova is seen in a nearby galaxy, it's sometimes possible to identify the star in earlier photos. So here we can see the star SN2005CS in ultraviolet. So when we look at the same star in the region of visual, we can see it over here, but in ultraviolet, we can see something is happening. And in infrared, we can see the star that became a supernova was a 10 solar mass red supergiant. Type 1 supernovae are about 6 times more luminous at maximum than type 2, and they fade more slowly at first. So in this image, we can see a type 1 supernovae decline rapidly at first and then more slowly. But type 2 supernovae pause for about 100 days before beginning a steep decline. Supernovae 1987A was an odd in that it did not rise directly to maximum brightness. These light curves has been adjusted to the same maximum brightness so we can compare the one to the other one. Here we can see the star that exploded as supernova 1987A had 20 times the mass of the Sun. Interactions of the burst of light and gas expanding from the explosion with material lost by the star during previous stages as blue giant and red supergiant have produced rings around the central glow, as shown in the high-resolution image and the artist's conception. The shock wave from the explosion is now expanding into a 1 light-year diameter ring of gas ejected roughly 20,000 years before the explosion. As that ring is excited, it is lighting up the region around it, revealing how the star shed mass before it collapsed. Supernovae typically leave behind shells of hot gas, expanding outward at velocities as high as 20,000 kilometers per second, and carrying away a fifth of the mass of the star. The shells can sweep up more gas from the interstellar medium and heat it to produce supernova remnant, and the nebula remains of a supernova explosion. So here we can see a supernova remnant is an exploding bubble of hot gas created by a supernova explosion. As the remnant expands and pushes into neighboring gas, it can emit radiation at many wavelengths. Jets can be seen exiting toward the left and right of gas A that we can see here. Supernova remnants look quite delicate and do not survive very long. A few tens of thousands of years before they gradually mix with the interstellar medium and vanish. The Crab Nebula is a young remnant, only about 960 years old and about 9 light years in diameter. Older remnants can be larger. Some supernova remnants are visible only at radio and X-ray wavelengths. They have become too tenuous to emit detectable light, but a collision of the expanding hot gas with the interstellar medium can generate radio and X-ray radiation. You saw in a previous chapter that a compression of the interstellar medium by expanding supernova remnants can also trigger star formation. So here is the image of our own galaxy, and here we can see at the far edge of our own galaxy is the remnant of the Crab Nebula, which is pretty cool to see. And this, ladies and gentlemen, brings us to the end of this lecture slide. Do you have any questions? So I assume there's no further questions. So the semester test next week is going to be all the work we do up until this slide. So this slide is the last slide of work will be on for next week's semester test. So I will upload the lecture recording now. I will also upload your mock test. Otherwise, good luck with your semester test you are writing at 5 o'clock today. And I see you all in Monday's class. Have a wonderful week and good luck with all your semester tests.